right, so I'm not recording. So now I'm recording. So welcome to Math 365. Talking about convergence. See me write some stuff on the board really quick. I've got the formula for the Fourier series for the square wave. We've got these formulas for the Fourier coefficients there. Okay. Last chance to join the Zoom call or look at someone's screen who is. Yeah, it takes a minute for you to pop up. Yeah, I've got Emma and Pylon. Yeah. Okay, so I think we are all here. Cool, thank you, everybody. And so now I just wanted to share the screen instead of projecting so I could also use the board. So let me show you something. I'm going to do this with Desmos. And so here on the screen, I've got this function. I'm actually calling the function g of x, and I'm calling the partial Fourier series f of x on Desmos. Hopefully that's not too bad. And so let's actually, well, I'll get to that in a moment. Let me actually modify the domain so it goes from -pi to pi instead of 0 to 2 pi. Okay, so there's our setup. And so yeah, you can see I've programmed in like an approximate Fourier series going out to 5, 7, 9, 11. So that's like 5 terms. And I'll show that in a second, but like I could even show you the first term, right? 4 over pi times sine x, right? That's the first one. So this is the first term of the Fourier series approximation for the square wave. I mean, it's already kind of like indicating it, right? 1/3 sine 3x. So that's already getting kind of nicer, and plus 1/5 sine 5x, and then you'll see getting closer. And adding on a few more terms, let's take a look. And you're starting to really see it. And the kind of questions that you get, yeah, question.
Do the like peaks on either side eventually go away? And if they do, how? Right? Because I've been watching for the last day just all these different like animations of Fourier series.
Yeah.
And I just don't understand how those peaks eventually go away because of the fixed endpoint. So at like that edge right there, there's going to be a peak where the signs all add up and there's nothing canceling it to bring it back down to 1. So like I'm just confused how it goes away and if it does.
Yeah, so the question is about these peaks right here. And this peak is at pi over 12. And so the question is sort of like, do they ever go away? And I mean, yes and no. So like probably they don't ever go away, but they get smaller and they start moving a little bit. So you're going to see a phenomenon that is what you're asking about. I think is the difference between pointwise convergence and uniform convergence. So like I think the peaks are always going to be there, but I think if you focus on like one particular point, like in the domain, like if you focus on this point, like 0.281, and then take more and more and more terms, then the red line is going to get closer and closer to the blue line. But the peak will still be there. It'll just maybe like shift over and start getting smaller. But your question is maybe like it can't get, so how could it get smaller? The way that it could get smaller is, remember, like sine 0 is equal to 0, and this is continuous function. So I think, well, let's see. Let's investigate a few more terms. But I see what you mean, because when x is like positive and small, then yeah, there is the Gibbs phenomenon, but for x being positive and small. Oh, I see. So where do you get terms that are negative? So it's coming from these, you know, like 9 times x, 11 times x, 40,000 times x. Those are what? They're horizontal shrinks. So you're going to get all these oscillations from sine, even in that like small fixed interval, that will give you negative numbers that'll contribute and sort of destroy the peak.
Well, it mostly just shifts it in towards 0, right?
Yeah, which is totally fine. That's totally fine. Because this we're kind of getting a little bit further into the conversation, which is fine. Like this convergence. So it's not quite correct to say that this Fourier series converges to your g of x, right? Because you know that you're always going to be hitting like 0 here, for instance. And you know that you always have to make that this partial sum is always going to be smoothly differentiable. So it has to sort of smoothly go from 0 all the way up to 1. And, you know, and then it'll come up too far and go back down too low. And so as you get closer and closer to adding on, you know, the infinity of terms, then this red part will like shift, as you say, closer and closer to 0, which means that, like again, if you fix any particular point on the blue line, the red stuff will run away and shift, and therefore it'll be like pointwise, coming closer and closer and closer. But the convergence won't be uniform, because you'll always be able to sneak in this tiny space between 0 and whatever, where you've got this like, you know, you have to at least go up distance 1/2, you know, to get from whatever small point near 0 you are to where you want to be, like up at 1. So you're seeing the difference between uniform and pointwise convergence. But if like I add more terms, yeah, these teeth aren't changing that much. So they are shifting. Before it was pi over 12, now it's pi over 16. The y value was 1.18. So let's continue to look. Yeah, Halloween's coming up. So 1.18. So still, that y value is not coming down. Add 2 more terms.
Does that my sawtooth series automatically?
If you can find a way to program it, then by all means, let me know. But in terms of being able to prepare for class rapidly, you know, this is certainly serving the purpose. And so 1.179, so the peak actually decreased a tiny amount. So I'm not convinced, well, actually, maybe they didn't. Maybe that was just from the, software approximation. Something happening in chat, but I can't see it. Okay, yeah. Yeah. So I'm gonna, I mean, this is kind of like trying not to get into the Gibbs phenomenon. But yeah, that overshoot is called the Gibbs phenomenon. That's true. And so, like in your textbook, you've been asked questions like, look, so you're given the blue function. And you get asked questions like, to what function does the Fourier series converge? And like, I hope this helps you understand that question a little bit better, because the Fourier series is defined on the entire real line, whereas your blue function was not. So this is converging to something, you know, as you scale out, it already looks pretty good, like the square wave. And so, like, I can tell immediately that since this is a sine series, it's converging to the, well, it's converging to the odd extension, you know, like we mentioned, of this line from 0 to pi, like you extend it odd and extend it periodically. So, I mean, this Fourier series, once you figure out where it converges on the interval from like negative pi to pi, then you'll take the periodic extension, and then that's how it'll converge. Onward. So we've been talking about convergence a lot. So let's look at these theorems and what they say. And your first theorem, this is 3.14 in the Logan book. And please look at the book or my previous lecture on this for the precise statements, but for the informal statement is that if you have function f is piecewise smooth. So here's function f. If your function f is piecewise smooth, smooth meaning all derivatives of all orders exist, piecewise meaning you can partition the domain into a finite number of pieces, and when restricting the function to each piece, it is smooth, which is the case here. Then this is going to imply that the series, that the Fourier series, converges to f pointwise if x is a smooth point. And the Fourier series converges to will you let me use this notation? converges to the average of the left and right hand limits. Is not a smooth. So for precise statement, I mean, this is a precise statement, to be clear, but for a statement that includes definition of piecewise smooth and includes definition of this notation, see my previous lecture or turn to that page in the book. And so what this means is just the average of the left and right hand limits at that point. So since this function is piecewise smooth, this theorem does apply, and it says this Fourier series will converge pointwise at every smooth point. So that is to say, like if you fix an x down here, then the Fourier approximation, so here's the partial sum, like when you plug in that point into the partial sum and take the limit as n goes to infinity, the answer will be -1. Or you pick this point. You plug in that value for x into this series, and now you get like a series of numbers that depends on n. Take the limit as n goes to infinity, the answer will be 1. If you pick a non-smooth point, it'll converge to the average of left and right hand limit, which is average of -1 and 1. Which is 0. And in fact, the partial sums are on the nose equal to 0 at every point there. And right after this is some theorem 3.15 that says if f is continuous and the derivative is piecewise continuous. So I'll use CTS for continuous. F prime is piecewise continuous. Then this means the series converges to F uniformly. And this theorem does not apply to this situation, because F is not continuous. It's not continuous. You can see the jump discontinuity there. That doesn't mean that the convergence won't be uniform. It isn't, but it just means that the convergence is not guaranteed to be uniform. But certainly it won't be in this case. So go back and look. Go back and look. Share the screen again. And what's the difference between pointwise and uniform convergence? So if you pick, like if you zoom in and pick any point that you want, no matter how close it is to 0, then you look at the corresponding point on the graph, and as n goes to infinity, the distance between the point here and the red point there will go to 0. That doesn't mean that the distance from the peak to the blue line will be going to 0. It could just mean this peak is shifting over. But y'all all got out of that Zoom room double quick. And so the reason why this convergence isn't uniform is that, on the other hand, no matter how large you take n, there will always exist an x such that the distance between the x value on the red line and, the distance between the y value and the blue line is never going to be small. It's always going to be bigger than 1/2, for instance. So no matter how large an n you can pick, I can always zoom in and find some x value where the red line's like below 1/2. And that distance will always kind of be there.
So if we're making the Fourier series for anything the discontinuity, is it guaranteed not to be piecewise? I mean, uniformly. Is it guaranteed not to converge uniformly?
No. So the question was, if you've got a function that has a discontinuity, is it guaranteed to not converge uniformly? And that's not true, as far as I know. I want to just restrict ourselves narrowly to what these theorems say. So I'm looking for results, not for non-results. The non-results are actually kind of pathological and difficult, and I'm going to try to stay away from them. There's one more convergence theorem that's not in the book, but it's kind of important. So if f is L2 function, so square integrable, the square of f is integrable and finite on negative L to L, then under this weak hypothesis, that's all you need. It will be true. Well, f is L2, and you have like a complete orthogonal system, like you do have for this classical Fourier series. Then this will converge to f in the mean square or L2 sense, which is like saying that on average, those pointwise errors aren't that big, or like when you integrate those pointwise errors, that integral will go to 0. And let's look at it, because this square wave, it satisfies this theorem and it satisfies that theorem. This square wave is an L2 function. It is. Because the square of it is just the number 1, and the number 1 is integrable from negative pi to pi. So that means that this will converge in the mean square. So it doesn't converge uniformly because there exists, so for any n that you pick, no matter which approximation you pick, there will exist points x, such that the difference between the blue line and the red line is not going to 0. But convergence in the mean square sense is saying, like look, say that you integrate those differences. In other words, say that you look at the area under the blue line and like above the red line, right? And then look at the area of that. Look at the area under the red line here and like over the blue line. So just add up all these little areas that you see. And that's going to be some number. But as n gets larger and larger and larger, those areas are going to get smaller and smaller and smaller. So yeah, that peak might not disappear. So the distance from the peak to the blue line might stay 0.18 or whatever. But the area, the area line will go to 0. So that's what mean square convergence says. So these are kind of technical mathematical results. For square wave, you do get pointwise convergence, meaning you fix a point, and then that series will add up to the value f of x. The convergence will not be uniform, meaning no matter how good of an approximation you pick, you'll be able to find an x where the difference between the red line and the blue line is not small. But it will be L2, which says, okay, maybe you can find an x where the difference is not small, but if you integrate all those differences to get the area between the red line and the blue line, that area is, going to 0. So that's my intuition for those 3 convergence theorems. And so I claim to you that those 3 theorems are all you need to know about convergence. You just need to know, keep separate. F of x and its Fourier series are different things. The relationship between f of x and its Fourier series are given by these 3 theorems. If f is an L2 function, which it almost always will be, then at least you've got this bare bones thing that says you might not converge pointwise, but the integral of the error is going to be small. Integral of the square of the error is going to be small. And then these say, if all you need is piecewise smooth and you're going to converge pointwise unless you're at a point of discontinuity, then take the average, it's fine. This is actually great. This is like your bread and butter. And this one says, if you're continuous and you're lucky enough that the derivative is piecewise smooth, it's also all you need, you'll converge uniformly. There's lots of other kinds of convergence theorems for Fourier series with different hypotheses. You can go down the rabbit hole and look them up, but these are the only 3 that you need. For this class, I can promise you that. And I'll pause here and let's do. Yeah.
So if the whole piece on the square both discusses like integration over the interval AB, and I imagine for like the repeated functions we're looking at, AB might just be like 1 period.
Wait, state the question again.
Like this part. I guess.
So it's A is minus L and B is L. Yep. So the question was about how do you define the error in these contexts? And the answer is the bounds of integration are minus L to L. Because what you're doing is you're talking about a convergence on this interval from negative pi to pi, and because the function's periodic, it'll work for any other interval too. That's what's happening.
What about a case when we're not looking at a repeated function?
When you're not looking at a periodic function?
Yeah.
So this is developed to work on functions that are compactly supported. So that means that they're non-zero on some interval, or that means that sorry, it means that outside of some interval the function is 0. So for instance, like if you have some function here, or whatever, it goes down to 0, and so you want to do like a Fourier series approximation of this function. So your first step is to do a change of coordinates so that it starts at 0 instead of A. And so it's fine to do linear change of coordinates, whatever, you've got a new function. And then your second step is to either take even extension or odd extension, whatever is your pleasure. Just take like an odd extension. And then now find Fourier series of this. So it's not like this only works on periodic functions. It's much better than that. It works on any function that's compactly supported, but you do these little tricks to, to write it in this way. But we don't really, I guess, emphasize that so much in class.
Ways we see a lot in physics, like wave patterns stuff.
You see it a lot in physics because these standing wave solutions are very physical. So we like to break them down to the different frequencies. But if you had a function that was definitely not periodic and not compactly supported, and had non-zero values along the whole real line, you can still work with that, but you probably are going to work with something called the Fourier transform. But this particular theory wouldn't apply to that situation. So I want to give you a short homework assignment for over the weekend. So the assignment is, we evidently gave a Fourier series for the odd extension, right? So just find the Fourier series for the even extension of this square wave. You can see how to do the even extension, just reflect it over the y-axis. And to what function on the real line does it converge? And you must justify your answer with one of the three theorems. So my claim to you is that anything that like any kind of question like that, you really can do with the three theorems. And I do want to show you a couple other things. I guess I spent longer on this than I hoped, but I prepared some other examples too, so I'll at least show them to you. So you can take, for instance, f of x equals absolute value of x. So long ago when I introduced this for the first time, I took f of x equals x, so odd extension. So here's f of x equals x, absolute value of x. And on the shared screen, you can see that I've taken absolute value and shown you two more periods. So I've shown you the true even extension. And so let's kind of look at the Fourier series, or like an approximate Fourier series for this. And so since this is like an even extension, the Fourier series is going to be a cosine series. So I'm only going to get these cosine coefficients, and I've actually worked them out for you. So A naught is going to be what? It's the integral from negative pi to pi, 1 over pi, absolute value of x times cosine 0 equals 1. So you can see that here. Of course, that integrates to pi. And so that means for my Fourier approximate series, the first term is a naught over 2, which is pi over 2. So there it is. What's my second coefficient? Integral from negative pi to pi, but it's even, so I'm doing 2 times integral from 0 to pi, x times cosine x. Here, this is n pi x over L, but L is equal to pi, so they cancel. And I just worked out this integral numerically. There's the approximate numerical answer. So you see me actually copy that down in here. And then the next one was 0, so that doesn't count. And then the next one, cosine 3x, and then integrating absolute value of x. So I got minus 0.14147106052, like whatever. So, but anyway, I just copied and pasted it to get this approximate Fourier series. So I did this totally with Desmos and numeric integration. It didn't take me that long. So I'm scrolling through and seeing the thing. So this is just a Fourier series with 3 terms. And look at that. So it came quite nice. So here there's less problems than there was before. I mean, like, yeah, we're not that close right here. But it's not like there's a peak that's running away, you know?
And it's really close to the bottom.
Yeah, so this convergence to me is looking like, I mean, you can't tell convergence by looking at one partial sum, to be clear, but this is looking to me like the convergence is going to be uniform. You see, because it's not like it was before where you had this discontinuity and the function had to run up from 0 to 1 and you always had that space. And yeah, and so you can apply this theorem 3.15, which says, look, this is a continuous function. The sawtooth is continuous. And its derivative is piecewise continuous. Its derivative is the square wave, right? And so therefore the convergence will be uniform, and you're seeing that. Yeah. And so I want to go to one more example that I prepared for you. I want to give you an example of an L1 function. So this is a function that's L1, but it's not L2. So it's integrable, but it's not integrable. So if I take 1 over the square root of absolute value of x, and I look at this on the interval from 0 to 1, so yeah, I'll just keep this in words for now. So I did this on the interval no, I think I did this on interval from 0 to pi, excuse me. So I looked at this function square root of x on interval from 0 to pi. And go ahead and integrate this if you want, and you'll find it's easy to do, and the answer is finite. So in other words, the area under the curve, you know, the part that's extending up to infinity is summable there. You can see it gets really thin really fast. But if you take the square of this, you get 1 over x, and 1 over x is not integrable from 0 to pi. No, it'll give you natural log is the antiderivative, and so it's not an L2 function. The integral will be infinite. So but you can still take the Fourier series, and you can ask whether or not this Fourier series converges. And we have no information from our theorems. So I want you to just think, not like, you know, don't make your brain like the Macintosh logo. It's just think when you've got no information, you know. So, and just kind of leave it at that. But you can still write down the partial Fourier series, and that's what I did. And so I computed all these coefficients for you before class. What's like and this is even extension, so it's just cosine series. So what's like A1? You would be doing something like 1 over 1 over pi, except maybe like 2 over pi, you'd integrate from 0 to pi, and then what would you do, like 1 over square root x? Cosine x, yeah, dx, and then 8.843988. So you see I've truncated it a little bit, but you're seeing how I'm getting these for sure. And so then I took 1, 2, 3, 4, 5 terms. So, and here's what I got. Here's what I got. So remember, this is supposed to go from 0 to pi, so from 0 to 3.14, and we're not guaranteed to be, you know, close after that. But compare this to the convergence for the other ones. Like the other ones at least looked reasonable, and this is unreasonable. So I'm not saying that this doesn't converge to 1 over root x. I don't know whether it does or not. Like maybe it does, but if it does, it's really slow. And this is an example of an L1 function. It's not L2. So the theorem doesn't guarantee you anything. And indeed, it looks kind of suspect. So sus. It's a mess, but but I don't know. Okay, so I'll stop there because it's 12:06. But I hope that gives you some kind of perspective on what those 3 convergence theorems mean, how they're used. And it's also sort of like my implied warranty or guarantee for you that you really don't have to use anything else but those 3 theorems to do the work in this course. So thank you, everybody. Have a great weekend. And I'll see you on Monday. Take care.